Then we will at the end introduce a little bit of equilibrium and all. We'll start equilibrium, which is chapter 13. So,
Yeah.
but first we'll spend some time doing some exercise questions because this is important. Uh, so let's look at it. There's chapter problems, that section, right?
Yeah.
So chapter problems and multi-concept problems, we'll look at these. So for example, let's start with question number 12.110. Okay,
1 0. Yeah.
12.110 in the book. This is the initial rates listed in the following table were measured in the methanol solution for the reaction. Okay, so there is C2H4Br2 plus 3I minus gives C2H4 plus 2Br minus plus I3 minus, right?
Mm.
So there is three experiments have happened. Initial concentrations for C2H4Br2 and I minus are given, and initial rate of formation of the product, which is I3 minus, is given, right?
Yeah.
Correct.
Yeah. Yeah.
We know rate should depend on K times something in this
Okay.
and something in this, right?
Yeah.
So rate should be equal to K times C2H4Br2 to the power X and I minus to the power Y. We don't know X and Y, and X and Y are supposed to be determined from the experiments.
Yeah.
So let's look at this and figure out the rate. So in the, okay, see, he's keeping I minus constant between 1 and 2, right?
1 and 2. Yeah.
And he's increasing this by how many times? That is
That is.
0.343. It is almost 3 times, but not exactly, right?
Yeah. Something.
Yeah.
Something slightly weird, but almost 3 times, right?
Yeah.
Let's find the ratio of this. 1.74, 17.4 by 6.45, right? See, it is 17.4 into 10 power minus 5 is the rate. And there it was 6.45 into 10 power minus 5, right? So
Yeah. It's a
almost 3 times that
it's
is
like
also increasing.
it's 2.7 exactly.
And this is also 2.7 it will be.
I think
The
so.
0.
Yeah. Yeah. It should be.
So 0.343 by 0.127 will be similar to the 17.45 divided by 6.45.
Yeah.
Yeah.
17.4 divided by 6.45. You can find the ratios by calculator. Just
Yeah.
find this ratio and this ratio, and that should be similar because
Yeah.
it is
It's like
coming close
around
to 3.
2.7.
2.69. Yeah. Same.
Yeah.
Both are coming same, no?
Yeah.
So that means if you increase the concentration by this many amount of
Yeah. It's
C2H4Br2, it is same,
same amount.
right?
So linearly.
So it is linear. So this is
Yeah.
1, right?
Yeah.
This is 1. And now let's look at experiment number 1 and 3, right?
Yeah.
Because you have to change I minus to find I power, right?
Yeah. Yeah.
Now, because we know it is linear, now it will not be difficult for us to do. You can say rate 3 by rate 1, right?
Yeah.
Should be equal to K will cancel, right? So it
Yeah.
will
Yeah.
become C2H4Br2 in 3 by C2H4Br2 in 1
In one. Yeah.
power 1 and I minus in 3 power y by I minus
Minus in one.
in 1 power y, right?
Yeah.
So these are now just numbers, right? You know the
Yeah.
values, and this is also a value. So basically you can find this ratio to the power y, right? I minus 3 by I minus 1 to the
Oh, yeah.
power
To the
y
power.
is equal to this into this by this, right?
Yeah.
So it is calculation intensive, but you can find it, right?
Yeah. Yeah.
You will be able to find the value of y,
Yeah.
Yeah.
right? If you use a calculator, you'll probably be able to find it quickly, but this is okay, right? So the rate law will come, right?
Yeah. Yeah.
The rate law will come in terms of the order and all will be known. Once order is known, suppose you know y is 2 or something, like whatever, right?
Yeah.
So then you can find the k value from any one experiment, right?
Yeah. Yeah.
Yeah.
Any one experiment you can take
So find the K. Yeah.
find the k, right? So that will also be known. And find the what is the initial rate when concentrations are both 0.15. That is obvious.
Yeah.
Part C is also obvious, no? Because once you find the rate constant, once you find the powers
Yeah.
here,
Yeah. Yeah.
initial rate is obvious, right? You can just put
Yeah.
Yeah.
concentrations, right? So
Like
12,
y we can find also by the method we used in the beginning, right? For x,
by how?
the
By changing
concentrate.
it a little bit.
Yeah. Oh,
Why? I mean, but the
I
data
get
is
it.
such that it is
Yeah,
not
data
obvious.
has changed. Yeah.
Data is such that it is not very like
Yeah. Yeah.
one thing is not being coming constant. No, you are
Yeah.
not
Yeah.
getting 0.127 of CH2H4Br2.
Yeah. I saw that.
So that is why you have to do the calculation. The method is the same everywhere. You have to use experimental data to find the values.
Yeah.
Right? Okay. This is this. Now, uh, let's look at question number 12.112. Okay.
Okay.
12.112. So he's saying the light stimulated conversion of 11 cis retinal to 11 trans retinal is central to the vision process in humans. So actually, when we do organic chemistry, we'll know that there are cis compounds and there are trans compounds.
Mm-hmm.
These are molecular formula is same, but the structure is different.
Mm-hmm.
Okay, so these are called isomers in general. Okay,
Yeah.
isomers are two compounds with same molecular formula but different structures, because of which their properties are different. So
Mm-hmm.
what we learn in organic is that structure determines reactivity.
Yeah.
Determines reactivity. So if the structure of a molecule is different, even if formula is same, its properties will be different. Okay.
Yeah. Yeah.
So this compound 11 cis retinal is becoming is transforming into 11 trans retinal.
Mm.
This is a compound that is present in our eye, and this is important for the vision process. So
Yeah.
it is light sensitive.
Mm.
So light is acting on it, and then it is becoming this, right? So what he's saying is this reaction also occurs more slowly in the absence of light. So now he's doing the reaction artificially. So
Mm-hmm.
at 80 degrees centigrade in heptane solution, the reaction is first order with a rate constant given, right?
Okay. Yeah.
So rate constant is K is given 1.202 into 10 power minus 5. K
Yeah.
is equal to 1.02 into 10 power minus 5. And it's a first order reaction, right?
Yeah.
First order. Then what he's asking us is what is the molarity of 6 cis retinal after 6 hours if its initial concentration was this, right?
Mm.
Correct. So
Yeah.
Yeah.
cis retinal was the reactant, right?
Yeah.
So after 6 hours, what will be its concentration if initial concentration is given to be 3.5 into
3.5.
10 power minus 3?
Yeah.
This is the A naught, right?
Yeah. Yeah.
And after 6 hours, so we have first order reaction, AT will be A naught
A naught into
to
e
the
to the
power E
power
power
k
minus KT,
minus kt. Yeah.
right? So
Yeah.
here this was given in per second and this time was given in 6 hours. So convert hours to seconds. It will be
Yeah.
6 into 3600 seconds, right?
Yeah. Yeah.
So you will just do E power minus KT. K is 1.02 into 10 power minus 5 into 6 into
6 in.
3600,
Yeah.
and then second cancel, right?
Yeah.
And this is two zeros. So
So 10 to the power
216.
minus 3.
216 into 1.02 into 10 power minus 3, right?
Yeah. Yeah.
So almost same as 216, so almost minus 0.2, right?
Yeah.
See, this is approximately, it will be that only 0.22, you can say, right?
Mm.
Right.
Yeah.
This
Yeah.
part will be almost 220, let's say, and this part will be
Yeah.
by,
It's
right?
220 only. Yeah.
So this is 3.5 into 10 power minus 3 into e power minus 22.
Yeah.
This is the final concentration. The questions in this book will need a calculator, but
Yeah. Okay.
in the
Mm.
normal books and IIT questions and all, you will realize that you will be able to do it yourself.
Mm. Okay.
So Now, then the second part is how many minutes does it take for 25% of the 11 cis retinal to react, right?
Yeah. So
So
we know
basically
not well.
25% has to react, right? So how much
Yeah.
is left is 75%, right?
Yeah. Yeah.
Yeah.
So you know that the left portion is 3 by 4 of the initial
Yeah.
portion,
Initial. Yeah.
right? This is what is left, right?
Yeah.
75%. So this is equal
And
Mm.
to
then put
A
it in
naught.
the equation.
Put it in the equation, you get 3 by 4. So log 3 by 4 is minus kt. So log 4 by 3 is kt.
Yeah.
So time is equal to 1 by k into log 4 by 3. Log 4 by 3 you can find yourself also, right?
Hmm.
2 log
Yeah.
2 minus log 3.
Yeah. Yeah.
So uh, so that is obvious. Then how many hours does it take? Okay, this is fine. This question is easy, right?
Yeah. Yeah.
Then 12.114. What fraction of the molecules in a gas at 300 Kelvin collide with an energy equal to or greater than EA when EA equals this, right?
Mm-hmm.
Okay, so this is the theoretical question. 12.114. So he's saying what fraction of molecules
In
of
a gas
molecules
at
at
300
what
Kelvin.
temperature? 300 Kelvin.
Yeah.
At 300 Kelvin collide with an energy greater than equal to EA. At 300 Kelvin collide with energy greater than equal to EA, right?
Yeah. Yeah.
Yeah.
Okay, EA value has been given to be from 50,
50 kilojoule per
50
mole.
kilojoule per mole.
Yeah.
50 kilojoule per mole, right?
Mm.
Now, when we were doing that Arrhenius equation, right?
Yeah.
So Arrhenius equation says that rate constant K is equal to A e power minus EA by RT, right?
RT. Yeah.
Here, there was a section where he was explaining the meaning of this equation.
Mm.
And
Mm.
what he explained was that this portion, right, is
Yeah.
representing basically PZ, something like this, right? PZE,
Yeah. Yeah.
right? Where P was a steric factor. Steric factor means are they in the right orientation? Z was
Yeah.
collision
Fraction of
frequency.
the. Yeah.
Z was collision frequency, right? How
Yeah.
many collisions per second?
Per second. Yeah.
And this fraction, this portion,
PZ2. That is the
the e power minus EA by
energy.
RT,
If
right?
enough energy is.
So what fraction of the collisions have greater energy than EA?
Yeah.
Which is what he's asking, right?
Yeah. Yeah.
What
Yeah.
fraction of collisions have energy greater than EA? So basically, you have to collide with greater than energy EA, then only you will be able to come close enough to react. Okay,
Yeah. Yeah.
because they will be facing nuclear repulsion as they move closer, right? You have to
Yeah.
start off with a kinetic energy that lets you get so close. Otherwise, they will just repel before this only. Okay.
Yeah.
So there is only going to be a fraction of collisions that have enough starting kinetic energy to get close enough, right?
Yeah.
That
Yeah.
is represented by this. Whether they are in the right orientation is represented by this, and how many collisions happen is represented by this, right? So
Yeah.
A
Yeah.
is equal to PZ, and this part is equal to the fraction, right? So this totally determines how fast the reaction can happen, right?
Yeah.
Yeah.
Basically, that tells you the rate constant, right? So now our question is basically just this much.
Yeah. Yeah.
So it is e power minus EA by RT. So minus 50 into 10 power 3 joule per mole divided by joule per mole. We have to be careful of units. Okay. So by RT is 8.314 joule per Kelvin mole into 300 Kelvin. So see, everything should have cancelled and now it is cancelled, right?
Yeah. Yeah.
It has to cancel, no? E cannot have a power where it cannot have a unit, right?
Yeah. Yeah.
Yeah.
So everything cancels now, and you have 300. This will become 10, and this will become 500. So 500 by 3 into 8.314, right? 24.9, right? correct?
Yeah.
So
Yeah.
it is
Yeah,
almost
yeah.
25, so almost e power minus 20, right?
Yeah, 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 yeah.
So it is so small. See, this will be huge, right?
Yeah.
This will be huge. So at 50 kilojoule per mole, right?
Mm.
The fraction of collisions that have greater energy than this is already quite small,
Yeah, yeah.
right? So you
Yeah.
can predict what will happen at 300 kilojoule per mole, right?
Yeah.
Correct.
Yeah, yeah, yeah.
Uh,
It's giving 100 kilo.
100 kilojoule per mole, right?
Yeah.
Okay. Uh, 1 second. Okay, awesome. Makes sense. So this portion becomes double, no?
Yeah.
Right?
Double. Yeah.
This is 100, it becomes 100, just two times, right? So
Yeah.
when it comes in the denominator, it will become smaller, no?
Smaller. Yeah.
So it
So
doesn't make
the
sense.
total is large.
Total is smaller, right?
Mm.
Are you understanding? If the activation energy was double, then the fraction of collisions which will have greater energy should be lesser, no?
Yeah. Yeah.
Yeah.
Right? So active, this is the fraction right now, okay?
Yeah.
But if you make this negative thing more negative, right? Then the
Mm-hmm.
fraction is
Mm.
obviously lower, right?
Yeah.
Yeah. Yeah.
So the rate of the reaction for that reaction will be slower, right?
Yeah. Yeah.
When activation energy is high, your reaction rate is slow,
It's slower. Yeah.
right? So it makes sense.
Mm.
Then then we go on ahead. Okay. Uh, so 12.116 is beginning with the integrated rate law, derive a general equation for the half-life of a zero order reaction. This we have already done in the theory,
Mm-hmm.
right? We already did in the last class that it is rate is constant for a zero order reaction, right?
Yeah. Yeah.
So
Yeah.
half-life will just depend on the K and the initial amount, right?
Initial amounts. Yeah.
Half-life is when initial amount becomes half of original, right?
Yeah. Yeah.
So A naught by 2 will be equal to AT, right?
Yeah.
And rate is equal to K times A naught, right?
Yeah. Yeah.
So
The,
dA by D, so you can do it. We have already derived it.
yeah. Yeah.
So
Yeah.
12.116 is clear. Then 118. Okay, let's do 118.
Mm-hmm.
Consider the reversible reaction. Uh, okay, reversible interconversion, first order interconversion of two molecules A to B and B to A, right?
Yeah.
AF is given, KR is given, right?
Yeah. Yeah.
AF and KR are basically rate constants for the forward reaction and rate constants for the backward reaction.
Yeah. Yeah.
We'll see in the next chapter that a reaction does not go to completion, but instead reaches a state of equilibrium with comparable concentrations of reactants and products if rate constants have comparable values, right?
Yeah. Yeah.
What are the rate laws for forward and backward reactions? Okay, so let's do this. So suppose A is like this, and like this, B, and this is Kf and this is Kr, right? Now
Yeah.
he's saying that is a this reaction is a reversible first order interconversion. Okay, so
Yeah.
this is reversible is clear from here, and it is first
Yeah.
order interconversion of A to B and B to A, right? So
Mm.
if you think of the rate laws for the forward reaction and backward reaction, so rate law for forward should be equal to Kf into A, right?
Yeah.
Power 1, right?
Yeah. Yeah.
Because it
Yeah.
is first order. And rate of backward reaction should be equal to Kr
R
in
into B
B, right?
per one. Yeah.
Because for
Yeah.
backward reaction, this is the reactant, right?
Yeah.
So at equilibrium, what happens it at equilibrium, the forward rate and the backward rate become equal.
Yes. Yeah.
Okay.
Reaction is equally fast in both the directions, right?
Yeah. Yeah.
Yeah.
So initially, if you think about it, the reactant mixture is mostly just A, right? Initially, when you start the thing, right, you have
Yeah.
A, right? And
Yeah.
Yeah. Yeah.
so A concentration was high initially, so rate was high initially in the forward, right?
Yeah, yeah.
B was 0, so rate was 0 in the backward, right?
Backward, yeah.
Mm.
However, as the reaction proceeds, more and more B has been forming, right?
Yeah,
And
yeah.
Yeah.
A is reducing. So forward reaction rate is decreasing, backward reaction rate is increasing.
Increasing, yeah.
And
Increasing.
eventually
Yeah.
these two rates will match at some level, right? So that will
Yeah.
mean that
Yeah.
KFA power 1 will be equal to KR B
B power.
power 1, right?
Yeah.
Therefore, at equilibrium, this is happening. At equilibrium, you will have Kf by Kr is equal to B by A, right?
Yeah.
Right? So
Yeah.
this is a constant, right? So this
Yeah.
constant is called capital K, which is equilibrium constant. So for this reaction, you will say that B by A at equilibrium will be equal to a constant, right?
Yeah, yeah.
Yeah. Yeah.
Now, B by A is constant. So the ratio of B and A doesn't change, right?
Yeah.
So if you increase B, A will also
A will,
substantially
yeah,
change
decrease.
so that K remains same at equilibrium,
Hmm.
right?
Yeah.
Yeah.
So now think about it. Because this K value, capital K, is dependent on Kf by Kr, right?
Yeah, yeah.
If Kf was much, much greater than Kr, right?
Yeah.
Then this ratio is much greater, very high value, right? Correct.
Yeah, yeah.
So
Yeah.
then at equilibrium, B is much higher than A, right?
Yeah, yeah.
So that means what? That the reaction has gone almost 100% forward, right? Gone to completion almost, no?
Yeah, yeah.
Because B is much higher than A, right? At equilibrium.
Yeah.
See,
Yeah.
Yeah.
equilibrium is like a steady state. Eventually, the steady state will be reached. Okay.
Yeah, yeah.
At that steady state, if your Kf was much bigger than Kr, let's take some examples. So let's say Kf was 10 power minus 3 and Kr was 10 power minus 9, right? So Kf by Kr is coming out to be 10 power 6, right?
Yeah.
So eventually the rates
Yeah.
will equalize, but what will happen is B by A will be equal to 10 power 6, right? Therefore,
Hmm.
B will be equal to 10 power 6 times A, right?
Yeah.
So
Yeah,
concentration
yeah.
of B will be a million times more than
More
concentration of
than,
A, right?
yeah.
So it might not even be detectable, this A, right?
Yeah.
Actually, the reaction is still in equilibrium, but the problem
But
is
it's
that you
just,
cannot see A.
yeah.
Like it's too less, right? So that is what we say that the reaction has gone to completion. Almost 100% has happened, right? Because we are failing
Yeah.
to detect the A, right?
Yeah.
Yeah.
If the reverse happens, if Kf is much lesser than Kr, right? Then reaction doesn't happen basically, right?
Yeah.
You will say that the reaction didn't even happen because it is actually happened. The reaction has happened and it is in equilibrium, but the value of B was so less. It was 10 power minus 6 of A, right? If we take the opposite values, right?
Yeah. Correct.
Yeah.
So B was almost a million times less than A, right? So if you started off with some concentration, you might not even be able to detect the B concentration, right? So
Yeah.
that will imply that nothing of the, you will say that reaction has not proceeded, right? It's not gone
Yeah,
forward.
yeah.
If your Kf and Kr are comparable, however, right, not very different from each other, then you will have reasonable concentration ratios of B and A, right? Then you will say that both B and A are present finally. You will be able to see both of them, right? Finally,
Yeah, actually.
right?
Yeah.
And you will say
Yeah.
that the reaction is in an equilibrium state, right? But actually,
Yeah.
any reaction will be in an equilibrium state. It's just that the compounds will not be detectable if it is too small or something, right?
Yeah, correct.
Okay. So that is what he is trying to explain here. So draw a qualitative graph that shows how the rates of forward and backward reaction vary with time. So let's draw a graph. Forward reaction starts off very fast, right? This is reaction rate. Okay.
Yeah.
And this is time. Okay. So reaction rate, forward reaction will start off quite fast, because it has A is initially a lot, right? And then it will slow down, right?
Yeah.
Why is it slowing down? Because finally
Finally, it's
equilibrium has been
reaching.
reached.
Yeah.
Hmm.
Equilibrium has been reached. So now A concentration is not changing, right?
Yeah.
At equilibrium, both the reactions happen at same rate. So concentration of nothing changes after a point, right?
Yeah.
So rate will become constant, no, a fixed value like
Constant.
this,
Yeah.
right?
Yeah.
The backward reaction starts from zero rate, right? It speeds up, and then starts to approach this, right?
Yeah. Correct.
Hmm.
This is backward reaction. And this is the state where equilibrium was reached.
Mm-hmm.
Equilibrium was reached. You understand?
Yeah.
So this is a qualitative graph.
Mm.
This is a high reaction rate for forward.
Yeah.
Okay. Then uh, part C. What are the relative concentrations of B and A when the okay, we have already done that.
Yeah. Calculated.
We did that B by A is equal to KF by KR.
Yeah.
KF by KR. So relative concentrations are these. This is the ratio.
Mm.
Okay.
Yeah.
Yeah.
Uh, okay. 12.120. Okay. This is carbon dating
Carbon
pressure.
dating. Yeah.
120. So the age of any remains from a once living organism can be determined by radiocarbon dating, a procedure that works by determining the concentration of radioactive 14 carbon that in the remains. So
Mm.
normally living beings have uh, carbon, a lot of carbon in their bodies, but in the
Yeah.
atmosphere there is a fixed ratio in which these isotopes are present, 12C6 and 14C6. There's also 13C6,
Yeah.
but 14C6 is radioactive with a half-life of 5,715 years.
50 years. Yeah.
So, and this is a first order reaction. It's a
Mm.
first order reaction. First order. Okay. First order, what is the reaction? 14C6 becomes 12C6.
12 seasons.
Yeah.
Okay. Uh, so, in the atmosphere, since there is all the carbon present, there is a slight component of 14C6 also. So, what happens as a result of that is that in living beings, it is maintained in a balance. The ratio
Mm.
remains fixed. The
Yeah.
ratio of
Yeah.
12C6 to 14C6 in living beings, it is fixed. But when the thing is dead, then what happens is the ratio can change, right?
Yeah. Yeah.
Because 14C6 will start disintegrating and there is nothing to replenish it, right?
Yeah. Yeah.
No process is happening which replenishes it,
Mm.
right?
Yeah.
So you're saying all living organisms contain an equilibrium concentration of 14C that gives rise to an average of 15.3 nuclear decay events per minute per gram of carbon. Okay.
Mm-hmm. Mm.
At when you're alive right now, you there will be enough 14C6 in you to have 15.3 nuclear decay events per gram of carbon per minute, right?
Yeah.
So what that
Yeah.
means is basically 50, on an average 15 molecules or 15 nuclei of 14C6, right, will be decaying into
12
12C6
C6 nuclei.
per minute per gram of carbon that you have,
Mm. Yeah.
right? So this is in a living being. This is the equilibrium rate at which this is happening in living things, right?
Mm. Yeah.
then then he's saying at death, however, no additional 14C is taken in, so concentration slowly drops as radioactive decay occurs, right?
Yeah.
What is the
Yeah.
age of a bone fragment from an archaeological dig if the bone shows an average of 2.3 decay events per minute per gram, right?
Mm-hmm.
So this was the rate right now. Rate at time t was 15.3 per minute per gram, right?
That's
Minute,
K, right? The rate
minute
of.
gram. Yeah, that is the rate of the reaction.
Okay.
That is the rate of the reaction. No,
Yeah. Yeah.
K is fixed. No,
Yeah. Yeah. Yeah.
K doesn't change. No, you understand?
Mm. Yeah. Yeah. I got
K
it.
will be
Yeah.
the half life. No, half life. We got that half life is equal to 0.693 by K, right?
Yeah, yeah.
So K is a fixed constant, and rate at the present instant, rate nu is 2.3, right?
Yeah.
Correct? So what you can say is how old is this you have to find, right?
Hmm.
So basically, you can say divide by that, right? You can say rate
Mm-hmm.
2 by rate 1.
Yeah.
Rate 2 by rate 1 should be equal to K times concentration of the nuclei by K times concentration of the nuclei at this moment, right?
Yeah, yeah,
2 by 1, right?
yeah.
Yeah.
So what we will have is ratio of concentrations now, right,
Yeah.
is going to be 2.3 by 15.3, right?
Yeah.
Is rate uh, a
Ratio
concentration
of
of
concentration.
A new by A original old, right?
Yeah.
So that will tell us, okay, so if you know this, then we can find from the first law rate order that A should be A naught e power minus kt, right?
Yeah. Then we can
Now
find.
A is A naught into 2.3 by 15.3 is equal to A naught into e power
Yeah.
minus kt, right?
Find it. Yeah.
You
Yeah.
understand?
Yeah.
So A naught will cancel, and
Okay.
you can find time from here, right?
Yeah.
So it will be log of 15.3 by 2.3, 1 by k is equal to time, right?
Yeah. And
Yeah.
And k can be found from the half-life that is given.
yeah, but in
K,
seconds we need to correct it.
minutes or seconds or years actually you should do, but fine. Doesn't matter so much. Uh, Whatever half-life is given in years, no, just write everything in years.
Okay. Yeah.
0.693 by 5715 years, right? So
Yeah.
per year. No, 5715 per
Half life is 5.
5715 years, right?
Yeah.
So this
Mm.
is your k, right? So when you do 1 by k, it will come out in years, right?
Yeah.
Yeah.
So
Yeah.
5715 by 0.693 log 15.3 by 2.3, right? Years,
Yeah.
right?
Yeah.
That should be your answer. So just quick recap. What happens is, suppose you have A and it becomes A dash, right?
Mm.
So rate law for this dA by dt will be minus k into A,
Into A.
right? So that is what I was doing. This is the rate of decay, right?
Yeah.
This was given to be 15.3 in alive things that are living and 2.3 right now, right?
Yeah. Yeah.
So that will be proportional to the old value of A and new value of A, right?
Yeah. Yeah.
That is how we found the ratio of new and old by taking this ratio, right?
Mm.
Once you have that, first order reactions, this will be the equation, right?
Yeah. Yeah.
On solving this differential equation, you get this as a solution,
Yeah. Yeah.
right? And because you know the old and new ratio, you can cancel out these AAs.
Yeah.
You don't need to know the
Yeah.
concentration. You need to know only ratio, right?
Ratio.
AT by A naught is what you need, right?
Yeah. That is E to the power
So
minus
that
K.
ratio we can find from this ratio, the rate of decay,
Yeah.
right? So that
Mm.
is how you do it. You can find the age now. Then, well, let's do 122. Assume that you are studying the first order conversion of reactant X to products in a reaction vessel with constant volume of 1 liter, right?
Mm-hmm.
At 1 p.m., you start the reaction at 25 degrees centigrade with 1 mole of X. At 2 p.m., you find that zero point 0.6 mole of X remains,
Yeah.
and you immediately increase the temperature of the reaction mixture to 35 degrees centigrade, right?
Mm.
At 3 p.m., this much remains. You want to finish the reaction by 4 p.m., but need to continue it until only 0.01 mole of X remains, right?
Yeah.
Okay,
Yeah.
good. So now you have to decide how much you have to increase the temperature again.
Temperature.
Right. What is the minimum temperature required to convert all but 0.01 mole of X to products by 4 p.m.?
Yeah.
And this is a realistic type of question. So you started off with 1 molar concentration, right?
Yeah.
Yeah.
So 122, you started off with concentration of the reactant, let's say X, initial is 1 molar, right?
One. Yeah.
This is at 1 p.m., right?
Yeah.
Correct. And you let the reaction happen at what temperature? At temperature of 25, right?
Yeah.
Temperature of 298 Kelvin. And you let the reaction happen for time is equal to 1 hour, right?
1 hour. Yeah.
And final concentration is
Zero
uh,
point 0.6 more.
0.6 molar, right?
Yeah.
So here Xt is 0.6 molar, right?
Yeah.
Okay. So fine. So now you know some information from this much, right?
Yeah.
You you have some unknowns, but you know some information also now, right? So you can
Mm-hmm.
say
Yeah.
Xt is equal to X naught e to the power minus kt,
KT.
right?
Yeah.
Correct.
Yeah.
So we can find out our k right now, no?
Yeah.
Right. So if you do the calculation here, you will get the k value at temperature is equal to
Temperature T.
298 Kelvin, right?
Yeah. Yeah.
Yeah.
Just do the calculation, then you will find this k value. Let's
Yeah.
call this for now, we'll call it K1, right?
K1. Yeah.
This
Okay.
one at 298 Kelvin, right?
Yeah.
This is now at 2 p.m. You have 0.6 molar of compound, right?
Yeah.
2 p.m. your initial, you can call this as a new initial, it is
Mm.
0.6, right?
Mm.
Now you change the temperature to 35, right?
Yeah.
At 3 p.m. 0.2 is there, right? 3 p.m.
0.2.
is 0.2, but temperature was 308 Kelvin, right?
Yeah. Yeah.
Temperature was 308 Kelvin, time was 1 hour, right?
1 hour. Yeah.
So you can find K at K2 or at 308 Kelvin from this data, right?
Yeah. Yeah.
In
Yeah.
the same way, following the same equation,
Yeah.
right?
Yeah.
So you know K2 and K1, then you can find activation
Activation
energy,
energy.
right?
Yeah.
You have this relation K is equal to A e power minus EA by RT, right? So
Yeah.
K2 by K1 will be e power minus EA by RT2 plus EA by
RTT1.
RT1, right?
Yeah.
So
Yeah.
it will become e power minus EA by R 1 by T1 minus 1 by T2,
And
right?
so LNK2 by K1.
So ln and all you can take and you can
Mm.
find the EA, right, from this.
Yeah. Yeah.
Once you know EA, you can
We
uh,
find the K for the last
uh,
reaction.
so you have to actually first find the K for the last reaction.
Yeah.
Then only you will be able to find the temperature, right?
Temperature. Yeah.
So you have starting at 3 p.m. you have this much, right? At 4 p.m. you want to end up with 0.01, right?
1. Yeah.
Yeah.
So 4 p.m. final concentration has to be 0.01 is equal to 0.2 into e
2
power
into per K.
minus k into
KT.
1 hour, right?
Yeah.
So this will give you the k required for this reaction to happen at this space, right?
Yeah.
K required, if you know, this is K3, right?
Yeah.
So your K3 should be equal to K3 by K2, right?
K3 by K2
Should be
is
equal to
e to
e
the
power
power.
minus same thing,
Yeah.
EA by 1 by
RT.
T3, T2 minus 1 by T3, right?
Yeah.
Correct.
Yeah. And by
This
R
is
is also.
308. This is unknown. EA is known from the previous thing. K3 by K2 is known,
Yeah.
and you can find it, right?
Yeah.
Yeah.
This will be the temperature required. So basically, he's asking you, uh, do you understand rate laws for first order, and can you find K from there? And do you
Hmm.
understand the Arrhenius equation? And it depends on temperature, right?
Mm-hmm. Yeah.
So if you change the temperature, your rate constant starts changing, right?
Yeah.
So once you change all of that, then you will be able to realize what is the temperature required that you need to raise it to in order to make the reaction go at a specified rate.
Yeah, yeah,
Correct? I hope everyone is understanding
yeah,
this.
yeah.
Yeah.
Okay. Uh, okay. So then next thing. Okay. So for example, let's look at 124. Some reactions are so rapid that they are said to be diffusion controlled. That is, the
Mhm.
reactants react as quickly as they can collide.
Okay.
Okay.
Yeah.
For example, an example is the neutralization of H3O plus and OH minus, which has a second order rate constant of this much, right?
Hmm. Hmm.
So the reaction happens as quickly as they can collide, right?
Yeah.
So if equal volumes of 2 molar HCl and 2 molar NaOH are mixed instantaneously, how much time is required for 99.999% of the acid to be neutralized, right?
Yeah. Yeah.
Basically, both of them will dissociate immediately and it will give 2 molar of H3O plus and 2 molar of equal volume. So finally, it will be 1 molar, okay? 1 second. So equal volumes of 2 molar HCl. So volume V, let's say, or volume say 1 liter. So we get 2 moles of H plus, right?
Yeah.
And similarly, you get 2 moles
Two
of
months of
OH
OH
minus
minus.
and 1 liter,
Mm.
1 liter. So 2 liters final volume, right?
Yeah.
So
Yeah.
final molarity has become 1 molar, right?
Yeah. Yeah.
So molarity of H plus in the final solution is what? 2 moles by 2 liters, right?
One and same for
1 m
OH minus.
and is equal to OH minus, right?
Yeah.
Okay, so this is the concentrations right now, right? And these are going to react with each other, and the rate constant has been given, right?
Hmm.
So you
Yeah.
have a rate of this reaction. Reaction is H3O plus OH minus gives 2H2O,
Yeah.
right? This is the fast
Yeah.
reaction, right? And it is a second order reaction, so obviously we should have this.
Squared. Yeah.
No, you should have this
Okay. Yeah. Like that.
like that, right? 1 1,
Yeah.
Mm.
right? It is not one compound, no, one
Yeah.
element
Yeah.
is not there, two different things are there, right? So but the convenient thing is that the concentrations are 1 1,
Yeah.
right?
Yeah. Yeah.
Concentrations are 1 1 and rate constant is given,
It's
so rate of the
given.
reaction is 1 1 and k, it's
K
just k,
only.
right?
Yeah.
So k value is equal to 1.3 into
1.3
10
into
power
10 to power
11
11. Yeah.
molar per second, right?
Yeah.
uh, 1 second, what is the unit?
Per molar per
Molar
second.
per mole per second, but mole will come, no,
Cancel.
molar will
Yeah.
come here. This is m minus 1 second minus 1, so when it cancels it becomes molar per second, right?
Yeah.
Yeah. Yeah.
So that will be the correct unit of a rate.
Yeah.
1.3 into 10 power 11 molar per second, right? Right.
Yeah.
Yeah.
So this reaction happens very fast, see, super fast. So finally you have to end up with how much is left. Uh, you have to time required for 99.999% of the acid to be neutralized. So what is left? 0.001
001. Yeah.
molar of acid should be left, right?
Yeah.
Yeah.
So that means uh, in the 2 liter solution, okay, 0.001 molar of H plus should be left over, right?
Yeah.
Right? This
Yeah.
this then only
Yeah. Yeah.
99.999% of the acid is gone, right?
Yeah.
Mm.
So you can just say that the reaction should happen. Rate is actually fixed, no?
Yeah. It is.
Rate is this. So actually, it is second order. So I mean, it is anyway instantaneous only almost. So how much has reacted? 0.999 has reacted, right? See, this was the initial rate, right?
Yeah.
Actual rate will be declining, no, as this decreases.
Yeah. Yeah.
You understand? So you have to use
Mm. Yeah.
the second order reaction expression, right?
Hmm.
The second order reaction expression was 1 by AT is equal to something. I don't
Yeah,
remember.
yeah.
1 by AT is equal to KT plus 1 by A naught or something like that.
Uh-huh.
Correct? Go back to the theory once.
Yeah, yeah.
See the second order rate equation. I think he has derived it. Second order rate equation. Second order reactions. We definitely derived it in class. It's just, 1 by AT is KT plus 1 by A naught, right?
Yeah, yeah.
So 1 by AT is equal to KT plus 1 by A naught. So now just put the values here, right? Like nothing you have to do.
Yeah,
Final concentration, you know, initial concentration, you know, right?
yeah,
Initial concentration was 1 molar, final concentration is 0.001, right?
yeah, yeah,
And
Yeah.
K is known, right?
yeah.
K is known. You don't do this, don't do what we were doing earlier, right?
Mm-hmm.
Because that is wrong. No, that is a second order reaction and the rate is changing, right?
Yeah,
This was only giving you the initial moments rate, right?
yeah, yeah.
You have to use the second order rate equation to find the concentration.
Concentration.
Yeah.
Okay. So this will give you the time because this K is constant and time will come here, right?
Yeah,
I hope that makes sense.
yeah, yeah.
Okay, what is part B of this? 1 second. Uh, Under normal laboratory conditions, would you expect the rate of acid-base neutralization to be limited by the rate of reaction or by the speed of mixing? Speed of mixing, no?
Mm.
See, the rate of reaction is super fast.
Yeah,
Speed of mixing, however, is not necessarily going to be fast.
yeah.
When you mix the acid, I mean, many of the acid molecules are not even touching the base right now. If you
Mm-hmm.
don't mix it very
Properly.
fast, right?
Yeah, yeah,
So the reaction happens much faster than what we mix it with, right?
yeah,
The rate
yeah.
of our mixing is much slower than the reaction
Slower,
rate.
yeah. Mm.
So actually, we have learned that when the reaction happens in multiple steps, the slowest step is what determines the rate.
Yeah, yeah.
So the slowest step or the rate determining step for us is the rate of mixing,
Mixing, yeah.
right? Okay, so this is fine. Consider the following data. This is easy. I hope you can do this.
Mm.
12.126 should not be a problem. You have some
Yeah,
data. The first and second piece of information gives you the order, right? Gives you the order. No, it is becoming 4 times. See, 22 into
yeah,
10 power
yeah,
minus 7.
Yeah.
It is a
Yeah.
second order reaction.
yeah.
When you double NO2, reaction rate has become 4 times,
Yeah, 4 times, yeah.
right? So it is a second order reaction, and second order reaction then how many seconds does it take for this much to become 0.001, right? You have to find the K of the reaction, right?
Yeah, yeah,
K of the reaction you can find by just putting it in one of them, right?
yeah.
Just by putting the rate is equal to K NO2 whole square, K will be found, no? Putting it in any one experiment's data, right?
Yeah, yeah.
Yeah.
But put it at the same temperature, 600 Kelvin, okay?
Yeah, yeah.
Okay, 600 Kelvin only put it in, and that is the K at 600 Kelvin, right?
600, yeah.
And if you
Yeah.
find K at 700 Kelvin, that will be two different Ks you will get, no?
Yeah,
See, the third experiment is 700 Kelvin data, right?
yeah, yeah.
So find rate at 600 Kelvin, find rate at 700 Kelvin, right?
Yeah.
That
And
will give
then
you activation energy.
activation energy, yeah.
And if activation energy you need know, then you can find rate at 650 Kelvin, which is the
Yeah,
question,
yeah.
right? So
Yeah.
find the new K because the final experiment that you have to do is
It's
at
at
650
650,
Kelvin,
yeah.
right? So that is why all this information is given because you have to find two different Ks, find activation energy, and then find the new rate at 650 Kelvin K, right?
Yeah, yeah.
Then after that, it is second order reaction,
Second
and
order,
the formula is 1 by AT is equal to KT plus 1 by A naught, right?
yeah, yeah.
And put that formula and you'll get the answer, right?
Yeah.
Okay. So I think this chapter is more or less fine. You should try the multi-concept
Multi-concept
problems,
problem.
and there are two, three you can try. It should be fine, right?
Yeah.
Are you guys understanding the whole chapter?
Yeah. Yeah.
Yeah.
Okay. Uh, then we'll go to equilibrium. Okay. This is chapter 13, uh, chemical equilibrium. In Allen, they are doing S block, P block, and all. No, what are
Uh,
they doing right now?
we haven't started S block equilibrium. We started equilibrium, but
Yeah.
You
we haven't
started
reached.
equilibrium.
Yeah.
Yeah.
We didn't do any kinetics before that.
So how are they explaining equilibrium?
So they just like they started with the basics of kinetics. Yeah. So like the rate laws and all we have done.
Rate laws and all you
Yeah.
read.
Yeah.
Okay. Okay, fine. So we anyway know now what is equilibrium, right? We
Mm.
know that. Let's look at the chapter section. So 13, chapter 13, first introduction. He's saying the state, chemical equilibrium is the state reached when concentrations of reactants and products remain constant over time, right?
Yeah.
So
Yeah.
why is the concentration remaining constant over time? Because forward and backward reactions are happening at the same rate.
Same time. Yeah.
So
Same rate.
nothing
Yeah.
much changes, right? Nothing much is going to change then, right?
Yeah.
Yeah.
Correct. So then, uh, okay, hold on for a second.
Yeah. Mm.
Huh, okay. Uh, yeah, so a mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Okay.
Mm.
In
Yeah.
this chapter, we'll address a number of important questions about the composition of equilibrium mixtures. Basically, what is the relationship between the concentration of reactants and products in an equilibrium mixture? And
Yeah.
how can we determine the equilibrium concentrations from initial concentrations, right?
Mm. Mm. Yeah.
So given initial concentrations, can we determine what will be the equilibrium concentration? And what factors can we exploit to alter the composition of an equilibrium mixture? Maybe
Mm.
we need a particular product. So we want to ensure that finally that product is formed, right, to a large extent.
Yeah. Yeah.
So can we do something to alter the concentration of a equilibrium mixture? It might not be forming as per we like, right? So can we affect some changes to the equilibrium concentrations, right? That is also
Mm.
something that we'll be
Mm.
doing.
Yeah.
So the last question is particularly important when choosing conditions for the synthesis of industrial chemicals like hydrogen, ammonia, methanol,
Mm.
and so
Mm.
on.
Yeah.
Like if you want to produce ammonia, then you need to do the reaction only under certain conditions, because only in those conditions will the reaction forward reaction be favored, right?
Mm.
Yeah.
And
Yeah. Yeah.
equilibrium mixture will have ammonia, right? You should not have some,
Yeah.
you cannot arbitrarily do N2 plus 3 H2 gives 2 and H3 and hope that a lot of ammonia will be there, right?
Yeah. Yeah.
Because it could be that the rate of the reaction right now at the temperature and pressure that you are doing it is such that ammonia is very negligible,
Less. Yeah.
right? So that is the whole point. So in 13.1, he's talking about rate of reactions. Again, look at the figure 13.1. So he's talking about this reaction. N2O4 is decomposing into 2NO2, right?
Mm. Yeah.
N2O4 is decomposing into 2NO2. And
Mm.
this reaction, he has first graph is concentration versus time of NO2 and N2O4. Now, at equilibrium, you will notice that concentration versus time graph also approaches some fixed values, right?
Yeah.
N2O4 concentration becomes constant after some time, right?
Yeah.
And NO2 also becomes constant after some time, correct?
Yeah.
So, but
Yeah.
these concentrations obviously don't have to be the same, right?
Yeah, they don't need to.
Um, what has to be same is reaction rate, right?
Yeah. Yeah.
Yeah. Yeah.
Reaction rate has to become equal, but the concentrations could obviously be very, very different, right?
Yeah.
Which is what we just
Yeah.
saw when we did rate by amount is equal to kf by kr, right?
Yeah.
Just now we did b by a is kf by kr, no?
Yeah.
So
Yeah.
from that logic, right, it could kf and kr don't have to be equal, right? So
Yeah.
b and a could be different.
Yeah.
So
Yeah.
now he is doing the reverse reaction also. Okay, if only NO2 is present initially, right, then the reverse reaction will also proceed and NO2 values will decrease. And
Yeah.
notice that in both the equations, both the
The
different experiments,
concentration is the same.
final concentration is the same,
Yeah.
right? So eventually, what is happening is N2O4 gives 2NO2, right? If you do
Yeah.
the reaction at the same temperature, pressure, everything, right? Under the same conditions, if you do the experiment in two ways, experiment one was done with only N2O4 from the beginning, right?
Yeah.
And experiment two was done with only NO2, right?
Yeah.
Yeah.
Eventually, both the reactions will approach the same
Same
equilibrium
concentration.
levels of
Yeah.
N2O4 and NO2, right? And in this case, NO2 is on top. Here, N2O4 was only present here, right? And NO2 was this graph here, right? And here NO2 was on top, but it declined till here, and
Yeah.
N2O4 went up till there, right? Eventually, you will approach the same levels in
Same
both the
levels.
graphs,
Yeah.
right?
Yeah.
Yeah.
Because the level or the ratio of N2O4 and NO2 depends on rate of forward reaction is equal to K times N2O4 and rate of backward reaction is equal to K times NO2,
And
right?
two.
Now, obviously, the powers could be something, right?
Yeah.
X and Y and whatnot, right? But this rate is equal to this rate means this ratio will be some fixed value, right? Forward and backward, right? Since at equilibrium rate forward is equal to rate backward, you will always have
Yeah.
the relation Kf N2O4 X is equal to Kb
Yeah.
N2 NO2 Y, right?
Yeah.
Yeah.
So N2O4 by NO2, the ratio, hopefully they are all both first order reactions. If they are both first order or both second order, then we can cancel the powers, right?
Yeah. Yeah.
And we can get a ratio directly, right?
Yeah.
Yeah.
N2O4 by NO2 to the power 1 or 2 or whatever, right? Is
Yeah.
equal to Kb by Kf, right?
Yeah.
So
Yeah.
the ratio remains constant in that case, right?
Yeah.
If
Yeah.
the ratio is remaining constant, then obviously we know that they have to reach the same levels, right?
Same levels. Yeah.
So that is what he is explaining here. In the second experiment, we begin with NO2 as the sole reactant at a temperature at a concentration of 0.08, right? The
Yeah.
conversion of NO2 to N2O4 proceeds until the concentrations level off at the same values as obtained in the first experiment.
Previous one.
Taken
Yeah.
together, the two experiments demonstrate that the interconversion of N2O4 and NO2 is reversible and that the same equilibrium state is reached starting from either substance, right?
Yeah.
So, strictly speaking, next paragraph, strictly speaking, all chemical reactions are reversible. When we sometimes call irreversible reactions, what we sometimes call irreversible reactions are simply those that proceed nearly to completion
Yeah.
so that the
Mm.
equilibrium mixture contains almost all products and almost no
No
reactants, right?
reactors.
For such reactions, the reverse reaction is often too slow to be detected, right?
Yeah.
So, why do the reactions of this and this appear to stop? Okay, obviously, we know why. Because both the rates are same,
Same. Yeah.
right?
Yeah.
So, nothing changes. It is not that the reactions have stopped happening, right?
Yeah.
They are
So
happening at the same
concentration.
rate,
Yeah.
right? Okay, equilibrium constant Kc 13.2 Kc. So he is looking at a general reversible reaction. AAB plus BB gives CC plus DD, right?
Yeah.
Okay, now uh, okay, so okay, first he has done an experiment. Okay, concentration data for the reaction N2O4 gives 2NO2, right?
Mm.
So let's look at that table 13.1. So
Yeah. Yeah.
initial constant, this is an actual experimental data, right? So
Yeah.
0.04 N2O4 initial and NO2 was 0.
Zero.
Then N2O4 concentration became 0.0337 and NO2 became 0.0125, right?
Yeah.
Yeah.
So then he is calculating the value of this equilibrium expression NO2 whole square by N2O4. Okay.
Yeah. Yeah.
If you find the value of this expression at equilibrium, so you have to do 0.0125 whole square divided by
Zero.
0.0337, right?
Seven. Yeah.
The value
Yeah.
comes
Yeah.
out to be this, right? 4.64 into 10 power minus 3.
Mm.
Yeah.
Then,
Yeah.
then he started with different concentrations, but ended up 0.0000 was the N2O4 and 0.08 was the NO2, right? Ended
Yeah.
up with the same equilibrium value, right?
Yeah. Yeah.
And then the ratio obviously of the expression came
Same.
same, right?
Yeah.
Now he
Yeah.
starts off with a different value of N2O4 starting, right?
Mm-hmm.
0.06, okay?
Yeah.
And now the values at equilibrium are slightly different, 0.0522 and 0.156, right? However,
Mm-hmm.
notice that the constant expression is still almost the same, right?
Same. Yeah.
Yeah. Yeah.
4.66, right? So
Yeah.
by this experimental verification, he is getting that this expression NO2 whole square by N2O4, right,
Yeah. Yeah.
appears to be related to the balanced equation for the reaction
Mm.
because 2 and 1 are appearing.
Two. Yeah.
Yeah.
So,
Yeah.
so when he got the reaction, N2O4 gaseous gives 2 NO2, right?
Yeah.
Gives 2 NO2 gaseous. He is getting that no matter what experiment I'm doing, starting with whatever amount of initial substances, right? I'm
Yeah.
always getting that NO2 whole square concentration by N2O4 is remaining fixed,
Mm-hmm. Yeah.
is remaining fixed. And this type of experiment was performed for multiple things. And what was realized was that there is a relation between the stoichiometric coefficients and this expression, right?
Yeah.
Yeah.
So
Yeah.
the moles that are here are coming in the powers, right?
Yeah.
So 1 is coming here, then 1 power 1. 2 is coming here, then power 2, right?
Yeah. Yeah.
So that leads us to uh, thinking that is there an analogous experiment expression with a constant value for every chemical reaction, right?
Mm-hmm.
If so, how is the form of that experiment expression related to the balanced equation for the reaction, right?
Yeah. Yeah.
Yeah.
So let's see, if you have AA plus BB reversible reaction CC plus DD, right?
Mm.
Then the expression that we should construct should be, see, product was on top in the numerator, right? So you have
Yeah.
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 C to the power C because C was the coefficient, D to the power D, right?
Yeah.
By A to the power A and B to the power B, right?
B. Mm.
Correct. This should be the expression that is similar in nature to this expression, right?
Yeah. Yeah.
The product comes first in the numerator, denominator has the reactants, and every element or every species that is present in the reaction, you have to raise it to the power of its stoichiometric coefficient,
Structure. Yeah.
right?
Yeah.
So,
Yeah.
and it is a plus plus becomes a product and all, right?
Yeah. Yeah.
Experimentally, it turns out that this value is constant at equilibrium
Mm-hmm.
no matter how
What?
you start with, right? You could have started with something else here and here, right?
Yeah.
You could have started with
Yeah.
some values of A and C, some amount of concentration of A and C, or B and D, or A and B, whatever, right?
Yeah.
No
Yeah.
matter what you start off with, obviously the values of A, B, C, D will be different in each case.
Yeah.
right? However, what
yeah,
is not different is the ratio of this.
Ratios. Yeah.
mm,
Okay. So this expression, right? This expression in 1864, see, on the basis of experimental studies of many reversible reactions, the Norwegian chemists Goldberg and Waag proposed that the concentrations in an equilibrium mixture are related by the following equilibrium equation.
Mm-hmm.
Kc is called the equilibrium constant, and the expression on the right hand side is called the equilibrium constant expression,
Expression. Okay.
right?
Yeah.
Here, square brackets indicate the molar concentration of the substance within the brackets, right?
Mm-hmm.
A-
Yeah.
And
Yeah.
hence the subscript C for the K, which says concentration, Kc, right?
Yeah. Yeah.
The substances in the equilibrium constant expression may be gases or molecules or ions in a solution, but may not be pure solids or pure liquids for reasons that we'll explain in section 13.4. Okay.
Okay.
So we'll read about why it should not be pure solids or pure liquids in this expression, right?
Mm.
The
yeah,
reason is that the concentration of pure solids and pure liquids is always same.
Okay.
If you think about it, water, what is the concentration? It will come out to be 55 molar.
Mm-hmm.
If you have a pure
yeah,
liquid water, no, always there will be this many molar per liter, no, moles per liter.
Yeah. Yeah.
So water concentration doesn't change, no, so you don't need to put that in that equation.
Mm, yeah. Makes sense.
So because you can take that constant concentration of water and put it down on the K side, right?
Yeah.
And
Yeah.
your K value will change, and what will be left will be only the molecules or gases
Molecules.
or
Yeah.
ions in a solution, right?
Yeah.
Not pure
yeah,
solid or not pure liquid. This
Yeah.
equilibrium equation is also known as the law of mass action, because in the early days of chemistry, concentration was called active mass.
Okay.
That is some old methods. You don't need to worry about that.
Yeah.
Equilibrium constant Kc is the number obtained by multiplying the equilibrium concentrations of all the products and dividing by the product of the equilibrium concentration of all the reactants
Yeah. Yeah.
with the concentration of each substance raised to the power of its coefficient in the
Coefficient.
balanced equation, right? So, no matter what the individual equilibrium constants may be in a particular reaction, right?
Yeah.
Particular experiment, the equilibrium
Mm.
constant for a reaction at a particular temperature always has the same value.
Mm.
This we already saw, we got 6 experiments he did on NO2 and N2O4, right?
Yeah.
Starting with
yeah,
different starting points, right?
Yeah. Yeah.
We ended up with different ending points also for the concentration for each of the species, right?
Mm-hmm.
But
Yeah.
the
Yeah.
ratio remains same.
Same.
Okay, this particular ratio. So values of Kc are generally reported without units because concentrations in the equilibrium constant expression are considered to be concentration ratios in which molarity of each substance is divided by the molarity in the thermodynamic standard state. Wait, what is he saying here? Values. Okay, so thermodynamic standard state, we know that is set of conditions under which thermodynamic measurements are reported. 1 molar concentration for each solute, 1 atm pressure for each gas, and specified temperature, usually 25 degrees centigrade, right?
Yeah.
We have done that in thermodynamics, no? This is the standard state.
yeah,
Yeah. Yeah.
So 1 molar concentration for each solute, 1 atm pressure for each gas. So here he's saying that the units are generally not specified in the Kc,
Mm-hmm.
okay,
Yeah.
because concentrations are considered to be concentration ratios in which molarity of each substance is divided by its molarity in the standard state. So
Mm-hmm.
so 0.0125 molar by 1 molar, molar cancels, and you have just a number, right?
Yeah.
So
Dimension.
basically, take a ratio of the standard state, right? So if the current pressure is something 2 atm, then you have to divide by 1 atm. In the standard state for a gaseous substance, it will be just a number. What he is saying is basically in the K value, right? Don't put the units, right?
Yeah.
yeah,
Normally assume that you are working with molarity. You have to work with molarity, pressure, in it pressure and at a particular temperature, and
Mm-hmm.
you are dividing by the 1 molar 1 pressure and all. It's just a
Yeah,
number that comes, right?
yeah, yeah.
yeah,
Equilibrium constants are temperature dependent. Obviously they should be temperature dependent because
Mm,
rate
yeah,
constants are temperature dependent,
yeah,
right? Kinetics rate
yeah,
constants are temperature dependent, no? So equilibrium constant should depend on temperature also, right? So the temperature must be specified when you say a value of Kc, right?
yeah.
So
mm,
here 4.64 into 10 power minus 3 is value of Kc at 25, right? And
Mm,
it is
yeah,
defined
yeah,
at 127, right?
yeah, yeah,
Now, the form of the equilibrium constant also depends on the way the equation is written, right? If you
mm,
write AA plus BB is CC plus GD, the equilibrium constant is this. If you write in the opposite way, equilibrium constant for that reaction is 1 by Kc, right?
yeah, yeah,
yeah,
Because you will write A power A, B power B by C power C, D power D, right?
yeah, yeah.
Right, that makes sense. So
Mm,
right now he's just asking you to write some equilibrium expressions. That is obvious. You can write it. NH3 square by N2 3H2, H2 whole cube, right?
mm-hmm.
yeah,
And N2 H2 whole cube by NH3 square, right?
NRC square.
Or just remember that don't put any solids and liquids, pure solids and pure liquids in the equilibrium
Yeah.
expression.
Equilibrium. Yeah.
Just remove that from it because the concentrations of that will be same throughout the reaction,
Mm,
and
yeah,
therefore that can be taken out and brought into the left side, right?
yeah, yeah.
And that will become a new k, the k dash or something,
Yeah,
right?
yeah,
Okay. Okay, fine. Then calculating the equilibrium constant, obviously if some data is given to you, then you can find the remaining things, right?
yeah, yeah.
So he's saying following concentrations were measured for equilibrium mixture at 500 Kelvin. Some concentrations are given, calculate the equilibrium constant. This is super
Mm,
obvious. You just
yeah.
put the values, right?
Mm-hmm.
Let's go on to the next one, K 13.2. Okay,
Yeah,
13.2. No, 13.3, right? 13.2 we just now did.
yeah. Equilibrium constant. Right?
1 second. Kc we just now did. Now we will talk about Kp.
KP. Yeah,
Okay.
yeah,
Uh, mm, okay, 1 second. There's some error in my PDF. Okay, fine. 13.3. Okay. Equilibrium constant Kp. So what he's saying is because gas pressures are easily measured, right?
mm,
Equilibrium equations for gas phase reactions are often written using partial pressures. You know
okay.
what partial pressure is, right?
Yeah,
If there is
yeah,
one
yeah,
container with multiple gases, partial pressure is the pressure that would have been exerted by just one of them
one of
if
the
you
gas.
had assumed it filled the whole container,
Yeah,
right?
yeah,
So if there are N2H2 and 3H NH3, right? There are
yeah.
three gases. If there is 1 mole of N2 and 2 moles of H2 and 3 moles of ammonia, right?
Mm-hmm.
Partial pressure will be mole fraction of that gas into total pressure.
Yeah, yeah.
It will be 1 by 6 of total pressure will be pressure of nitrogen, and 2 by 6 of total pressure will be pressure of hydrogen,
Hydrogen.
and 1 by 2 of total pressure will be the pressure of ammonia,
Yeah.
right?
Ammonia.
yeah,
So partial pressures and total pressure, you should know the relationship, and you should
Yeah.
know that it depends on as if the whole gas volume is occupied by one
By the
particular
one
gas,
gas.
right? So then you do the gas
yeah,
law formula to get the pressure,
Mm.
right?
Yeah.
So now the reason that you are writing k expressions using partial pressures instead is that in gases the easiest thing to measure is pressure.
Mm-hmm.
It's not easy to do concentrations of the gas, right?
Yeah.
Weighing the gas is harder than measuring pressure, no?
Yeah, yeah.
Right? Weighing the gas will be much harder, no? Concentration will need mass of the gas and
Mass
stuff,
of gas. Yeah.
right?
yeah,
So you will write the similar kp expression but use pressures instead of concentrations, right? So
Yeah.
it will be PnO2 whole square by PN2O4. That
Yeah.
will be your Kp, okay?
Yeah.
Where PN2O4 and PnO2 are partial pressures in ATMs of reactants and products at equilibrium. And
Hmm.
subscript P on K reminds us that the equilibrium constant is defined using partial pressures.
Yeah.
As for Kc, the values of Kp are dimensionless because you are dividing by 1
By one
ATM,
more. Yeah.
which is the standard pressure, right?
Yeah.
Okay, thus the units cancel. So constants Kp and Kc for gas phase reactions like this, AABB gives CCVD, right? Are
Yeah.
related, are obviously going to be related because amount of substance will be related, amount of the gas will be related to the pressure, no?
Yeah. Yeah.
So he's saying, uh, okay, so he's saying because the pressure of each component in a mixture of ideal gas is directly proportional to its molar concentration, right?
Hmm. Hmm.
So for component A, if you think, right,
Yeah.
partial pressure of A into V is NART, right?
Yeah. Yeah.
So
Yeah.
partial pressure is Na by VRT, right?
Yeah.
But Na
Yeah.
by V is the molarity, no?
Hmm. Hmm.
Right? Moles per liter is the concentration, no?
Yeah.
So partial pressure is equal to concentration of A into RT.
RT. Yeah.
And similarly, partial pressure of B and C and D are also concentration of BCD into RT, right?
Yeah. Yeah.
The equilibrium expression is therefore given by Kp is equal to, now see, instead of Pc and Pd, we will put CRT and DRT, right?
DRT. Yeah.
Right? And that becomes C power C, D power D by A power A, B power B, right?
Hmm. Hmm.
And RT to the power C plus D minus A minus B, right?
Yeah. A plus. Yeah.
Yeah.
Correct. So now what is C power C, D power D? That is Kc, right?
Yeah. Casey.
So you get the equation Kp is equal to AC, Kc into RT to the power delta N. Delta N is what? Number of moles of
Number of
products
moles.
minus number of moles of reactants.
Hmm.
Yeah.
C plus D minus A plus B would be number of moles of products minus reactants, right?
Yeah. Yeah.
So you have uh, here you have Kp is equal to Kc RT delta N, where AB plus B, wait, AA plus BB gives CC plus DD, right?
Hmm.
And
Yeah.
Yeah.
this reaction was, let's say, happening in gas phase. So basically, first you wrote your Kp expression in terms of pressures and converted pressure as pressure of A is equal to Na by V into RT.
RT.
So this becomes A RT, right?
Yeah. Yeah.
And this gave you the relationship, this one, right? Delta N is equal to C plus D minus A plus B.
Yeah. Yeah.
Okay. So
Yeah.
this is the relation between Kp, Kc. Now, obviously, now he's taking some examples and explaining how you can look at different situations. If your number of moles of products and reactants are equal, then delta RT to the power 0 it will become.
Yeah.
And then Kp and Kc will have equal values, right? So
Yeah.
for
Yeah.
reactions like H2 plus I2 gives 2Hi, right? You will have Kp is equal to Kc,
Yeah. Yeah.
correct?
Yeah.
Okay. Then, okay, relating the, this is easy. Uh, okay. Then we have heterogeneous equilibria. Heterogeneous equilibria and using the equilibrium constant, right? So heterogeneous equilibria is the same thing where you are saying that concentrations of solids and liquids are always going to be same, no?
Yeah.
Because
Mm.
look at the reaction CaCO3 gives CaO plus CO2, right?
Mm.
Now
Yeah.
CaCO3 is solid, CaO is solid, right?
Yeah.
And
Mm.
but CO2 is a gas, right?
Yeah.
Yeah.
When the reaction is carried out in a closed container, three phases are present at equilibrium: solid, solid, gas, right?
Yes.
Yeah.
So solid calcium carbonate, solid calcium oxide, and gas carbon dioxide, right?
Yeah.
If we
Yeah.
were to
Yeah.
write the usual equation, right, you will
Mm.
have to write all of them, right, together.
Yeah. Yeah.
So once again, though, the the concentrations in the equilibrium equation are ratios of actual concentration to concentration in standard state, right?
Yeah.
mm,
The A inside the equilibrium expression is a ratio of actual concentration to standard state concentration, right?
Yeah. Yeah.
Because the standard state of a pure solid is the pure solid itself.
Yeah. Yeah.
The
Correct.
yeah,
concentration ratio for a pure solid and also pure liquid is equal to 1. Okay, so the
Yeah.
concentration ratios
yeah,
of CaO and CaCO3 will be 1 because standard states of pure solids and pure liquids are themselves, right?
Yeah. Yeah.
So
mm,
these concentrations can be eliminated from the equilibrium equation and you get Kc is equal to CO2 concentration,
Mm-hmm. Yeah.
right? Analogous equation for in terms of pressure will be Kp is equal to pressure of CO2,
Pressure
right?
of CO2. Yeah.
As a general rule, concentrations of pure solids and liquids are not included when writing an equilibrium equation, right?
Mm.
yeah,
Because only those concentrations can change actually.
Yeah. Yeah.
Okay. So to establish equilibrium between solid, solid, and gas, all three components must be present. It follows from the equations Kc is equal to CO2 and Kp is equal to PCO2. However, that the concentration and pressure of CO2 and equilibrium are constant. Concentration and pressure, because it's equal to Kc and Kp, right?
Mm-hmm.
Independent of how much CaO and CaCO3 is present, right?
Yeah. Correct.
You understand? Because the Kc for this reaction is coming equal to the PCO2 or CO2 concentration, right?
Yeah. Yeah.
yeah,
So that means the CO2 concentration or CO2 pressure at equilibrium remains fixed
Fixed. Hmm.
as long as you don't change the temperature, right?
Temperature. Yeah.
So you could change the value of calcium carbonate or CaO in the thing, but your CO2 concentration will still be fixed, right?
Yeah. Yeah.
yeah,
If the temperature is changed, however, concentration and pressure of CO2 will also change because values of Kp and Kc depend on temperature, right?
Hmm. Yeah.
So
Correct.
now he's giving some examples of this situation where there is heterogeneous equilibrium. Why is it heterogeneous? Because there are multiple phases, right?
Yeah.
Homogeneous equilibrium would have been all gases or all liquids or all solutions, right?
Yeah. Yeah.
yeah,
Heterogeneous is when there is a mix of solid and gas
Solid and yeah.
or something like that, right?
mm,
So this
yeah,
is 13.4. 13.5 will be using the equilibrium constant. So 13.56 onwards we will do in the next class. Okay. Next class we'll
Okay.
try and do as much as left, till 11.
Yeah. Yeah.
Okay. Just read it up. It will be fine. You will be able to understand it.
Yeah.
Read 5, 6, 7 types. You will see what is
Mm.
happening. There is a principle called Le Chatelier's principle that also we'll have to understand. Otherwise, it's fairly straightforward. You should just read it.
Yeah.
Okay.
Okay. Okay.
So Thursday we'll do this, and Tuesday is our maths class.
Yeah.
Okay.
Yeah.
Rahul
yeah,
took a class on Friday, no,
Yeah.
yeah,
for physics, right? So
Yeah.
you guys have
mm,
some homework on rotations.
Yeah.
yeah,
Okay. So fine. Uh, he will schedule his rotation class. This week will be probably the end of rotation, right? For you guys.
Yeah. It is.
yeah,
It's he's taking the class on Saturday.
He's going to take next week Saturday.
Yeah.
yeah,
Okay.
And the
Fine.
week after is actually the school exam. So that week,
yeah, the whole week.
Okay. Okay. So we'll adjust what whole week as in every day is exam.
yeah, every day
Yeah,
is exam.
Okay. So we'll do extra classes after that.
Yeah.
Okay. So till Saturday, however, we'll do classes. Okay.
Yeah. That's fine.
Okay.
mm,
That's it for now then.
Yeah. Hmm.
Bye.
That's
bye, so.